coming to us and share your knowledge and your experience on deploying Kamailio on these, let's say, dynamic environments, Kubernetes. Thank you.
Thank you. Great to be being here, and thanks. So, where did we start? We were running a proprietary cloud for use as a service. Just a background of for us, we started in 2000 being an innovation hub for the carrier group we belong to, and started UC as a service as one of our products in 2005. Just a little history. We were providing a multi-tenant voice over IP platform based on a commercial solution as the background. And we have a typical growth of 4,000 to 6,000 ports in Austria per annum. And our vendor, which we used underneath the platform, launched its own cloud product and wanted to take over our customers, which we didn't like. So we started to investigate and look for a vendor lock-free solution. Sorry. And with that, we came up with a new stack using Kamailio, Asterisk, and Kubernetes for scalability to be ready for the future. In the old architecture, we had a lot of shortcomings we learned over the time. We had very complex routing, SIP and prefix-based, with a high risk of Big Bang updates. Since there were a limited number of clusters from the commercial vendor, we were locked into their cycle of upgrades. We had no customer-level scaling or service-specific scaling, so we were completely bound to the cluster infrastructure and the unit of work from the provider we were using. It had specific hardware requirements. We had very high external software and hardware costs, as well as the risk of the external dependency, which we really learned the hard way, since licenses and regulation changed on a one-sided way, and we were limited to specific phone hardware. Just to give you an understanding of the cost structure, in the end, 68% of what the customer paid was actually given to the third-party vendor, which provided the infrastructure solution. And then, so we came up with a new architecture. I hope that's visible, or it's not too small. So we chose to go for a dedicated namespace for a per customer base with the dedicated pods on a customer base, and also to have full resource isolation and reservation from a customer perspective. We tried to use the Kubernetes services for load balancing and redundancy where possible. We will see later that for RTP and SIP signaling, that is not necessarily always true, that you can rely on these techniques, since they're very web or HTTP oriented. This is why we introduced what we call the dynamic router propagation or route controller, which is a component sitting within the Kubernetes cluster, which keeps track of all the resources and deployments happening there, and redistributes that information across our signaling stack, so that all components are aware and know how to route properly. There are other shared components where it's not necessary to have some individual deployment on a per customer base. The other part which comes with Kubernetes, yes, there are ways to work around that, but we stuck with the design which comes out of the box, which was there's network separation. So you have an internal cluster network and you have your external network, and your worker nodes are the linking components between the networks. Yes, and the complete part is fully auto-provisioned, the environment. In the end, we can work on bare metal and have automation for every layer of the infrastructure to build up automatically, which is very important for us for also disaster recovery. So now that we have a little bit of an introduction and the overall architecture, we want to take a deeper look at the part of the SIP routing and the challenges we faced and how we solved them. I hope there are some insights for everyone here. So you typically have, as said before, the network separation between the cluster internal network provided by the CNI within Kubernetes and your external network within your data center or the cloud you're using, as well as then the edge, so internet traffic. We wanted to make sure that the traffic is routed freely within the environment so that we can have short and optimized paths if there is customer-to-customer communication as well. We learned that the Kubernetes ingress, which is the way to get the data into the cluster, is very optimized for web traffic and does not take real-time traffic as well as the signaling traffic into account. Yes, and then we learned that you have a very dynamic world of SIP destinations, and we need to announce them to all the SIP routers or border components. So how did we solve that? In the end, what we call dynamic routing strategies or liquid SIP routing orchestration is nothing else that we build all the Kamailios which are part of our SIP routing architecture and made them aware of the topology from the outside with no downtime route reconfigurations. And we also try to do some automatic path optimization so that we reduce latency, which is a very important part because people don't want to wait too long for the call to be ringing, be connected, or have any other updates. And for our architecture, we chose to make Kubernetes the single source of truth. So we take all the information for the routing stack from within the Kubernetes cluster and deploy them outside. I hope that's not a bit overloaded. This is a simplification of the architecture just to have all the moving components inside. So you see we have the redundant SBCs, which are the real border elements. That can be connectivity to fixed core, IMS, SIP trunks, whatnot. And then the first layer of importance is what we call the routing application service. Also here simplified, but in the end, it's we have multiple VRRP pairs of Kamailio services. Each of these services have their private and local installed key value store for all the necessary or for the dynamic information. Kamailio does not update the key value store by itself. We have an external service which also runs on the same node, which updates the information. More on that later. And then the next layer, which is then actually on the edge of the Kubernetes worker nodes, what we call Kasico, which is the Kamailio ingress controller. And here we also added a RTP engine as a side to have RTP traffic flow correctly, then in and out of the cluster. And underneath you see the back-to-back user agent, which are just distributed across the clusters, always with a placement on different nodes for redundancy purposes. We have then, within the cluster, we only have one key value source because we decided if that sort of resources drops and the connectivity, we have a much bigger problem than just SIP routing. And then the last part, the bottom component, the routing coordinator, is actually a pod running within the Kubernetes API, monitoring the Kubernetes API and subscribing to all sorts of events, adds of nodes, removal of nodes, add of pods, removal of pods, and new placements, and so forth. And that is then distributed over the green layer, which is a message bus distribution. We're using nets for that. So how does the route and application server by itself works? We did some performance tests and found that using the Kamailio config with no external logic, so no KMI, led to the best performance and the most stable environment we could find. We also learned that we cannot have any network dependency outside of the Kamailio, because then you can end up in the lock situation that you wait, that you time out, you run out of threads, and so forth. So we chose to move the key value store to each of the Kamailio nodes. So therefore, even if there are no updates being populated across the network anymore, the service by itself still works autonomously with the last information known. So that's number-based routing, location-based routing, access, and so forth. Yes, we chose to, for redundancy reasons, to use them in VROP pairs with a SIP heartbeat as well as a key value heartbeat, because for us the service is only available if both of these services are running, and then it should switch over to the passive node if there is a failure, which allows us in the end to do updates during complete peak times with no interruption of service. And then we wrote an additional service which monitors the network and the messages to keep the local key value store in sync. So the benefits we saw from this architecture actually is Kamailio only reads from the key value store. There's no write operation, and we can reduce the timeouts to very low limits because we assume the service is running on the same node, so there's no network, no other dependencies. And Kamailio does not need to process the NAT messages, even though there is a module. How does that look a little bit in reality? So a new call would come in. Also, these are all simplified parts of it to just illustrate the overall working. So we have an incoming call. The first part is we need to do the main number lookup and identify the tenant namespace, because we said each customer, each tenant has its own namespace, so a completely isolated environment on the Kubernetes side. So the first part is that lookup. You see we have the main number here, and then we see, okay, it is enabled, so actually that's an active customer, and then we have the Kubernetes identifier, which is just a namespace name, and then we have a dispatch group ID number. So we're using a dispatch module to have an individual dispatch group per tenant, which identifies the Kubernetes edge nodes to actually forward the traffic accordingly. So the second part of the setup is then the dispatch lookup. So we have that unique identifier. We look up the dispatch group. Also here in this example, it only points to one of the worker nodes to just illustrate the part. The rest of the setup is what you know of the dispatch module. And therefore, then the traffic can flow to that proper node. Another part of the dynamic routing is if a new customer is added. So the customer is a self-service portal. They can create themselves a new customer or a retail partner or whoever that is based either on a user interface or an API. In the end, the routing controller sees the new resources, the back-to-back use agent, so Asterisk pod is being deployed. As soon as that happens, we distribute across the messaging bus that information to the routing application service, to the Kamailio ingress controller, and as soon as that has happened, and the main number is known, you can actually place your first call. All in all, that takes about 3 minutes to have a complete customer setup, including basic calling when the number is known ahead of time or can be provisioned out of a pool of available numbers. The last part is the environment by itself is dynamic. So there can be all sorts of reasons why an Asterisk pod or the back-to-back user agent would die on one of the nodes. In this case, on our node 1 of the Asterisk dies for one specific customer. We immediately remove it from the key value store, populate it across the environment. So yes, with the decision to have an individual key value store per Kamailio, there's only eventual consistency. So it takes a little bit of time to distribute that information. In the end, that's milliseconds, but it's still a little delay. As soon as that has happened, the dispatch module knows to no longer forward traffic to the still existing nodes for that customer. I think it was customer C to a different node. And then based on the automated scheduling and placement, in this case, our tenant back-to-back user agent Asterisk would be started on the node with the number 2. As soon as that happens, we put them back into the database and redistribute the information across the node, and we are in full high availability mode for all the call processing. While this happens, actually, we distribute the state in the background. So also buys or other events on the signaling would continue to work, just being routed to the new node. So that's mainly about the SIP routing and the dynamic nature we came up with to work with that highly volatile environment. The next part is looking a little bit into RTP routing part. So to save bandwidth and to use, let's say, the resources valid, we try to use direct media when possible. For us, direct media doesn't only mean between phone-to-phone direct media, but also SBC, RTP engine, SBC, or phone, or whatever combination. We try to keep the RTP traffic, when possible, out of the Kubernetes cluster, because first of all, there are some network and latency issues and routing parts you don't want to necessarily work with. There are solutions and it works, but we feel like we can utilize the resources, the hardware way better if we run that outside. But there are still cases where you do want to have the media traffic within the cluster. This is the early media part where you really need your back-to-back user agent to bridge the traffic and be within that. We also use it in cases for recording service in specific scenarios, as well as music on hold. I'll show a little bit of a complete dialogue with the RTP traffic and the RTP engine being part of it, with our slight adaptation on a few things. Also, again, it is simplified to work on a slide. I hope we can follow along. So we have a normal invite coming from the SBC to the routing application service, which then decides to go to which worker node. As soon as that has happened, we get our first SDP invite. So here, the important part is we introduced a new media type, which we called proxy media. This is actually the originating IP address of the node where the traffic came in. And the other part is we keep in the normal media type audio, in this case, the originating SBC. This is a very important part to consider because later on when we want to do direct media, we cannot lose that information. But the only component aware of that information from an SDP perspective is actually the edge component of the Kubernetes cluster, the Casico. So this is part of the ingress controller we deployed. So in this case, we actually said, okay, we would not take the shortest path to the Asterisk on the local node, but to another one. So we actually have additional east-west traffic, which happens here. We do send back the traffic to the Kamailio where it came in. It would not be necessary because we are completely running all the Kamailios in stateless mode. Sending back to the RAS, sending back to the router. And now we are doing the second part. So we are inviting our desk phone and a new dialog. And again, so yes, there are a lot of lines and a lot of stuff. We see that the SDP offer we sent out actually has the SBC outside number, and the other one now has the IP address of our desk phone. These are all non-routable IP addresses because this is an MPLS scenario, but in the end, you see we actually bridged a direct media connection between the SBC and the phone in this case, even though we had early media in between, where we routed the traffic with our proxy media type across the network. I hope that makes any sense. Else feel free to ask later. So what are the takeaways here? We needed the RTP proxy on the edge for media bridging. That's due to the part that we can send RTP traffic from within the cluster out. The default Kubernetes logic would just send the data out from the node your pod runs, which is the source. But in the SDP message in your offer, you provide an IP address which is not reachable from the outside, can be ignored. More important, what we found is also the port is not correct. So you will see devices which actually reject the RTP traffic for security reasons if the offer does not match the reality who is actually sending the package. We have other systems which actually do learn and adapt their knowledge of the RTP traffic accordingly. To make it correct, we introduced the RTP proxy and the communication between the Kamailio and the RTP proxy to really offer the SDP correct. Yes, and with that, you can have, it might be interesting to have shared media endpoints outside, but you don't need to. You can still send the ML music on hold from within the system or bridge early media and other traffic scenarios where you have RTP flow, which you cannot direct from point to point. So, what are our conclusions from it? Kamailio and Kubernetes actually yield a lot of potential, both from the operational and commercial benefits, but you have to design carefully and be aware of the slightly different designs and architectures which are involved. And we also learned, we followed the strategy of automating everything to have a consistent and reliable deployment. And also don't be afraid to listen to the Kubernetes or monitors and the events and really use that to your advantage and dynamically route your traffic and keep your system in sync. So many thanks for listening. Any questions?
Thank you, Florian. Interesting architecture. So we have Ihor here.
Yeah, thanks. One question, you are using RTP engine in a kernel mode or in the user space?
We use it in this case at the moment in user space mode. From the containerization, we have also been playing with a more deeper integration on the node level to actually be able to use it in kernel mode and have a sort of a shim pod on top as the daemon set, which then talks through to the operating system. But that has some security implication since you can route through from, let's say, the pod level into the OS level of the worker. So that's...
Second question.
Okay. Thank you. Okay, thank you. Yeah, yes, related to again, we did try to use Kamailio with RTP engine in cloud, and Kubernetes was one of the technologies that we tried, and our experience was not very good for two reasons. One was related to RTP. Packets are UDP and very small, and Kubernetes is not very good with UDP. We observe, especially if the RTP is compressed and it's small packets, it just ignores it or drops it. And on the SIP side, if we try to use, of course, it requires server-side NAT to be implemented because the Kubernetes has private IPs and so on. So if we use the natted server-side NATs, the SIP message becomes too large and we have the fragmentation issue. We did solve the fragmentation, but the RTP was still bad. Sometimes when there is load, it starts dropping the RTP packets and the customer have problems like breaking voice or choppy voice, the words are being cut. How was your experience? Did you have any such complaints, or how you solved this?
One of the answers for the RTP is we try to keep as much RTP traffic out of the cluster as possible. Yeah? That is the solution there. There are some tunings depending on your CNI, what you want to do. It starts on the connection tracking part. It's some eBPF changes on how to manage it, but it depends a little bit on your CNI. For the signaling, we chose not to use server-side NAT. We actually use a SIP domain routing pattern, which is a little bit more lookup, but we have a unique SIP domain name per tenant customer, and we actually use that to route the traffic, and we propagated the knowledge of the IP addresses so that we actually do the, let's say, topology hiding or the NAT translation on the Kubernetes edge without really doing it. Yeah? So from the outside perspective, it looks like you have a single SIP signaling destination. Yeah? And inside, we then retranslate the domain to the internal domains of the Kubernetes side, send it to the back-to-back user agent. Here, we have a forward proxy setup done, which distributes again, and then sends it forward. So that's actually the solution we took to actually reduce the number of headers and sizes.
Okay, thank you, Florian. And it's time for the coffee break. But before, one more device. Ramona, can you pick a name?